Confidence intervals. Here we are looking for an interval where we are confident that the mean of the population lies if we know the mean of a sample of size n. We assign a percentage to the confidence, usually 90%, 95% and 99%. Those are very standard ones. 90% of scores are within 1.645 standard deviations from the mean. So what we're talking about here, if we have a normal distribution like this, and this is the standard normal, which is Z, which is a normal with mean 0 and standard deviation 1. Then if we have a symmetric interval like this, so that 90% is in here, then this is negative 1.645 here and 1.645 here. So in other words, plus or minus 1.645 standard deviations, since the standard deviation is 1. And we can use this for other distributions by doing 1.645 multiplied by whatever their standard deviation is. Now, for 95% confidence interval, it's 1.95996 standard deviations. We normally just use 1.96. And for a 99% confidence interval, 2.58. In general, if we have confidence level, lower boundary, upper boundary, for 90%, so what we're doing here is creating an interval with x bar at the middle. So we have x bar take away 1.645 times the standard deviation. Now we've discussed the x bar and the sigma over root n before. For 95% we just change the number of standard deviations to 1.96. For 99% we change to 2.58. We can now predict with a level of confidence the range within which the mean of an entire population lies if we know the mean and standard deviation of a sample of that population. The mean of the population mu will be equal to the mean of the sample x bar. We will assume that the standard deviation of the population sigma equals the sample standard deviation multiplied by the square root of the sample size. So that's just reversing what we did going from population to sample mean. So sigma would be Sx times root n, and then that means we can use these confidence intervals here. So we can see how it's constructed. For 90% we're using 1.645 again, 1.96 for 95, 2.58 for 99, and this time we're multiplying Sx root n, which we're using to estimate the population standard deviation.